Welcome everybody. It's lovely to see so many with us here today at this webinar, Community Wastewater Reuse with High Rate Algal Ponds, Professor Howard Fallowfield. This is our second webinar on this topic, and there's been such a high interest that we've had to run a second one. My name's Trevor Pillar, National Partnerships Manager with IceWarm. Well, it's great to see so many here, and we are so looking forward to today. But just in terms of logistics, a little bit of making sure everybody's on board, there's an icon below. If you could just click the icon that says raise hand, I'll just know that everybody's there. And then when I see it raised, thank you, Andrew. Yep, and others are coming on, Angela, Sarah. Yep, Tim, that's great news. Thank you for that. You can put them down again, that's fine. Just wanted to make sure everybody could use those facilities, and that raise hand is all about asking questions later on. If you raise your hand, then we'll uplift you and you can come on screen and ask questions. There's also a Q&A button in case you don't have audio or visual. You can click on that and begin to ask questions already. Tim, thank you for your question. Okay, we'll get on to that. That's great. That's excellent. Ask questions early, ask them often, and we'll have a great Q&A time after it's finished. All right. I won't read all that on the screen, except to say number 5 at the very bottom, we're going to run a 2-day course. There's been such popularity about this, and that 2-day course will talk about a number of comparisons between old wastewater schemes and new community wastewater schemes that Howard Fallowfield is actually running. So yeah, I'll just point out that last one, then there's plenty of webinars there. But today we've got a 25-minute presentation, then 25 minutes Q&A open to everybody. Once again, as I said, get your questions in early, get them in often, and if you can come on screen by raising your hand, even better. This will be recorded today, and we'll send the recording out to everybody. While I'm on that, we'll also send out the PDF of what Howard talks about. His PowerPoint will be sent out to everyone in PDF. And stay on board. As soon as the webinar is finished, you'll get a screen flick up to fill out this feedback. It's the way we shape our future webinars, so all your comments will be welcome. Howard is an aquatic microbial ecologist. Her research focuses on the health aspects of water quality and has had 25 years experience in the UK and Australia designing, constructing, operating, evaluating performance. It's much sought after by many organisations who are looking at their wastewater treatment, including abattoirs, councils, other government bodies and private bodies, rural communities mostly. Well, I'm not going to read that whole thing out, but we understand the depth and breadth of your experience, Howard, and we're so glad that you've been able to come and join us today. Over to you, Howard. Thank you.
Thank you, Trevor. I'd like to thank IceWarm for extending the invitation to present this webinar, the second one on the application of high-rate algal ponds. And this is, as I say, the second webinar, and we'd like to move on. And I've been particularly asked to talk about mechanisms and the future of high-rate ponds, so we'll press on right away. Now, I'm aware that some of you may not have attended the first HRAP 1. It is still available at that IceWarm site, and you can catch up with it at your leisure. But I figure it's important just to make sure we're all on the same page about what we're talking about with South Australian community wastewater management schemes. In South Australia, where there's in communities where there's potential issue about disposal of septic tank effluent. So in rural communities, often they don't have centralised wastewater treatment facilities. They depend on on-site treatment facilities, which is often the septic tank, and the treated effluent from the septic tank is disposed of to soakage trenches. And where the soil conditions aren't conducive to disposal of that effluent, we retain the septic tank in the backyard. We allow settlement and flotation, 24-hour residence time, and then the liquid phase, rather than being disposed on site, is sent to a lagoon system, which is classically a 5-cell lagoon system, a facultative pond. More frequently or more often they're known as waste stabilization ponds worldwide, and it's a 5-cell design, with the first pond system being a facultative pond and then 4 maturation ponds in series. Facultative pond is a 36-day residence time, and the combined residence time of the 4 maturation ponds is 30 days, leading to a 66-day residence time all up. Some of the systems around South Australia. This is one that we would be visiting with the on-site, with the course that's going to be run in November, where we can visit these sites. This is a typical waste stabilization pond in the Barossa Valley. So we have initially anaerobic digestion in the septic tank. The solids are retained in the tank. It means then that we're only piping liquid phase. We're not piping solids, so we can have cheaper engineering, smaller pipe diameters, leads to a lowering in the capital costs for these systems. And the liquid phase, as I say, is delivered to these 1.4 meter deep unmixed systems with long retention times, leads to large surface area requirements and a relatively high capital cost where you've got land available for these systems. What we've been looking at with the Local Government Association of South Australia and Loxton-Waikerie District Council is the idea of replacing the 5-cell waste stabilization pond system with a high-rate algal pond. And a high-rate algal pond is a mixed shallow system, 0.3 to 0.5 meters deep. It's mixed by a simple paddle wheel. It has shorter retention times because, as I'll show you through the webinar, the reaction rates are really much higher in these sort of systems. It has a small surface area requirement because the residence time is so much less. Because that residence time is less, it also means that there's less evaporative loss of the water, and also you decrease the capital cost because you've got a smaller area requirement, smaller earthworks, etc. Our work with Local Government Association and Loxton-Waikerie District Council led to the system being independently validated by Australian Water Quality Centre, a national accredited testing facility, and this then led to the design guidelines for high-rate algal ponds as an element of wastewater treatment trains to be issued for application in South Australia. I should say that the validation was done consistent with national guidelines, and we're going to talk a bit more about that. And those national guidelines are also consistent with World Health Organization guidelines. So what we're going to talk about now is the application of these recycling guidelines to natural wastewater treatment systems. These guidelines have been applied in Australia through most of the large metropolitan activated sludge plants in the major capital cities, but there's been very little done on these natural systems, lagoon-based systems are out in rural communities. And I think this is one of the first that have used these guidelines to enable the natural system to be validated. Okay, so the natural wastewater treatment systems, the guidelines we're talking about here are the Australian National Guidelines for Water Recycling, Managing Health and Environmental Risks. And this is promulgated by the National Health and Medical Research Council in 2006. It employs the same concept used by the World Health Organization of disability-adjusted life years. So it's looking not just at mortality associated with exposure to enteric pathogens, it's also looking at morbidity and loss of income and general well-being. And the tolerable risk is accepted as 10 to the minus 6 DALYs per capita per year. And that's equivalent to an annual risk of diarrheal illness of about 1 per 1,000 people. So what happens with this, the risk is associated with the exposure to waterborne pathogens, because even though we treat the wastewater, we've still got to dispose of the wastewater. In South Australia, these systems tend to be disposed of to irrigation of woodlots, horticulture, agriculture, if the effluent quality is sufficiently high. And what happens is there is health-based performance targets derived to ensure that we don't exceed that risk of, or that DALY of 10 to the minus 6 and the annual risk of 1 in 1,000 people. And these guidelines are centered around the idea of log reduction values. And log reduction values are really accepting that the class of organisms we're concerned about are all enteric pathogens, bacterial, viral, and protozoan pathogens. We measure the concentration of the organisms in the incoming wastewater stream. We can measure it then as it changes throughout the treatment train to the final effluent quality. And we then just measure what went in, what went out, take what went out away, the numbers of the organisms, the concentration of the organisms that went out away from those coming in, and that gives us our log reduction value. And there's a requirement to meet certain log reduction values. It also takes into account the idea that you have to be adversely affected by wastewater. You have to be firstly exposed. The wastewater has to have pathogens that will cause disease. You have to be exposed to them. You have to ingest a volume of the wastewater. Ingestion volumes used in the risk assessment are variously between 1 mil and 50 mils. and you have to be susceptible to the organism. And all these are taken into account in arriving at these health-based performance targets. So as I said, the community wastewater management treated effluent is most commonly used to irrigate non-food crops, typically eucalypts and woodlots. And the target log reduction values that we're looking for this application are 5 log reductions for viruses, excuse me, because they can come in at 10 to the 6, 10 to the 7 per 100 ml, 4 log reductions for bacteria, and 3.5 protozoa, things like Cryptosporidium and Giardia. And additionally for this, the guidelines stipulate that we have to have less than 10,000 E. coli per 100 ml. We don't use medians or means for the log reduction values. We use the 5th percentile. That's the worst case scenario, if you like, in terms of when I go on to talk about how this is actually physically done. It's we take 20 samples, and that's really the answer for the worst. The answer is the worst sample that you actually take in the 20 when you talk about 5th percentile values. So we measure the log reduction values through the treatment train, but also for approval or validation, we take into account how that treated wastewater is used during public irrigation. So we talk about distances, setback distances. They are distances between the disposal field for the wastewater and any adjacent property that might be adversely affected. We talk about excluding the public from the times of irrigation, so we would only irrigate at night when it's unlikely the public would be present. And we talk about subsurface irrigation increases your log reduction value because you're not aerosolizing pathogens and increasing the potential for exposure by the public. The enteric pathogen indicators used in our validation was E. coli, which is the classical one, I suppose, for wastewater indicator organism for enteric bacterial pathogens. FRNA phage, which is a non-human pathogen. It's actually a virus that infects E. coli. It's used as an indicator. There's very cheap, robust methods for detection of this organism, and it also gives you some insight into how viral pathogens may be inactivated in your treatment system. The big problem organisms or group of organisms are pathogenic protozoa, things like Cryptosporidium and Giardia. It's in these small systems, it's unlikely you're going to have enough numbers coming in from the small population. It's unlikely the population will be infected with these organisms. Therefore, you won't have them coming into your coming into your treatment plant, and you can't measure a log reduction value if you don't have the organism present. And following consultation, we used aerobic spore-forming bacteria as a surrogate for pathogenic protozoa. This was all done in consultation with the Department of Health in our Department of Health and Ageing in South Australia. And for these validations for natural treatment systems, the view is, of course, that we're relying on natural factors such as light, temperature, to affect treatment and affect pathogen inactivation. And you'd expect that the worst case and the worst performance of these natural systems would be in the winter. So the validation is a conservative validation. It's done in winter conditions. As I said before, we were just running the system. It was done by an independently accredited lab, and it's done by taking 20 inlet and 20 outlet samples. It's taken on Mondays and Thursdays to take into account any differential flow or differential activities within the communities over a week, and it's over a 10-week period. And then, as I say, the fifth percentile log reduction values are then determined as the performance value for the validation. And these are some results of the validation. I've presented the means, the standard deviation of the mean, the median, the percentile, and then the 20 samples that were taken. And the system the system I'm showing here is a 10-day HRAP pond validation. And what you can see, 10 days. What I'd like to compare is the picture I showed you of the Lindock waste stabilization pond, the unmixed waste stabilization pond. The pond that we were comparing our HRAP pond with had a 30-day residence time, and the log reduction value for that was 2.1 compared to 3.3 in the winter in a high-rate algal pond. And you can see that that is significantly a significant difference of over 1 log removal in terms of means. The 5th percentile, which, as I said, is the highest the lowest log reduction value, of the 20 samples taken over the 10 weeks becomes your 5th percentile value, and that's still 1.8, which is very close to the mean of the waste stabilization pond operated over a year. I would draw your attention to aerobic spore-forming bacteria. They are not a good surrogate for Cryptosporidium in these natural systems, and we published a paper with Paul Young, one of my PhD students, which is referenced below. And what we showed was it's likely that these spores are being blown in from agricultural soils nearby, and the negative value means we were seeing more aerobic spore-forming bacteria coming out of the treatment plant than was going in the influent. And we had to find we had to identify why this was the case, and it's likely, as I say, either wind-blown soils containing the organisms coming into the system, or it's naturally occurring spores in the influent wastewater that are actually germinating within the system and increasing the numbers within the wastewater. So that's a bit of a side about the use of aerobic spores. They're used in drinking water systems, but they're not a good indicator for natural wastewater treatment systems. So the question now, which is where I want to move on to, is why is the LRV greater in the high rate pond at the much shorter retention time? And as we said, retention time equals larger impoundments to retain the wastewater. It leads to increased capital costs. So understanding or providing a rationale for why this is the case is important. So what I've called this section is a primer on the mechanisms of microbial inactivation or die-off in natural wastewater treatment systems like waste stabilization ponds and high-rate algal ponds, to try and give a basis for why high-rate ponds are so much more efficient. So the first slide, really, we're considering a waste stabilization pond, and the water depth in a waste stabilization pond is in South Australia, it's recommended to be 1.4 meters deep. And when you have sunshine and you get infrared, you get the surface water is heated up, it's less dense, it stays on the top. You get colder, more dense water at the bottom because there's no mixing of the system. It's sitting out in the Australian summer, and you can get a thermocline where for every meter change in depth, you might get 1 degree. The largest difference we've seen between top and bottom of a large waste stabilization pond in Adelaide is 12 degrees. And that's quite enormous, really. 12 degrees in 1.4 meters means that you're changing reaction rates for both the growth of algae and the growth of bacteria. You're changing all the physical constants for diffusion, etc. So a 12-degree difference is quite enormous. That situation will remain as long as there's no mixing. The less dense water will stay over the colder, more dense water unless you have wind action, and then you get destratification. The wind starts to mix the waste stabilization pond, and you'll get the colder anaerobic water because oxygen diffusion rates have been lower through the body of the water. You get the anaerobic water mixing with the aerobic water, and you start to then get a more homogeneous pond. But it's not an ideal reaction environment for wastewater treatment, and particularly for modeling wastewater treatment and understanding performance characteristics. I'm going to show you the video now, which I think is shows why a high rate pond is significantly different. It's got a simple paddle wheel mixing that's turning at about 12 RPM. This is our system that we built for Melbourne Water out of the Werribee treatment plant to look at nitrogen removal and also biomass biosolids production. Shallow line pond, this is only 0.3 to 0.5 meters deep, mixed by a paddle wheel. And you can see also that it's got a channel divider. So we're really controlling the hydrodynamics in the pond. And if we look throughout the depth of that pond, it's homogeneous throughout the depth in terms of dissolved oxygen, temperature, and pH. So you've got a much more homogeneous reaction environment. Sorry. And of course, if we start looking now, when we've got that in a high rate pond, we're talking about a high rate pond only being between 0.3 and 0.5 meter deep. When we talk about log reduction values, the primary agent for inactivation of viruses and die-off of bacteria is naturally occurring UV light. Now, of course, the water industry is used to high-pressure mercury vapor lamps and things that produce wavelength down at 254. Natural sunlight, of course, UVC does not penetrate through the atmosphere, so we don't get any UVC. We don't get the short wavelength UVC penetrating down to the Earth's surface. What we do get is UVB, And another PhD student of mine, Natalie Bolton, did a lot of work on photoinactivation of E. coli, adenovirus, and FRNA phages. And she made some really initial measurements, first measurements that really had been done on UV penetration in these systems. And what you find is the shorter wavelength only penetrates, the UVB only penetrates to about 3 centimeters into the water body. We have another wavelength, which is UVA, goes to about 7 centimeters on average in the water bodies we measured, including waste stabilization ponds and high rate ponds. And then we also have visible light, which goes to 0.14, 14 centimeters through the depth. And that's pretty near 50% you will have light penetration. So here, the rest of the, if you were not mixing, this means that half of the pond would be in the dark, would not be exposed at all to this irradiance. But of course, in a high rate pond, we're actually mixing. And what we can do, and we've got modeling has been done on this, and we now have a model of inactivation and die-off being influenced by UVB, UVA, and visible light that includes a mixing component. And of course, what you're doing is you're bringing dark water that would, if in an unmixed situation, would remain in the dark, particularly when it's stratified. You're actually bringing that water up, putting it through the disinfection irradiance levels where organisms can be damaged by UV, and returning it. And this is ongoing, and it's mainly due to the paddle wheel and the shallow depth that we've got in the pond. And the measurements we've done show that the inactivation rates are so much higher in a high rate pond compared to a waste sterilization pond.
5-6 minutes, roughly. Yep.
Okay. Issues that, other factors that come into play when you're actually mixing the pond is, of course, in a high rate algal pond and a waste sterilization pond, you're really depending on algae for a degree of treatment. And the benefit of algae is they photosynthesize, they produce dissolved oxygen, and the high rate ponds can be between 200 and 300% saturated in the daytime. That oxygen is available for the heterotrophic bacteria to mineralize and respire the organic carbon, and in return they produce carbon dioxide, which is then used by the algae for photosynthesis. And of course, when you use carbon dioxide, you actually elevate the pH of the water, and daytime pH values can be up to 8 to 11. And this combination, mediated by algae and bacteria, this combination of a very high pH and a very high saturated dissolved oxygen level leads to reactive oxygen species, which will also start to damage cell membranes and cause increased inactivation and cell death. So when we're talking about UV, we're looking at UVB in the short wavelength, UVA, visible light, 400 to 700 nanometers is what we measure. UVB directly damages DNA. UVA has an interesting interaction with bacteria. You can have sensitizers in the bacterial cell that react with these oxygen species and cause photooxidation inside the bacterial cell. If you're talking about viruses, you can have external photosensitizers that are in the wastewater, very high levels of oxygen and reactive oxygen species being produced, and they also damage the membranes, causing cell death. So where you've got increased exposure to UV irradiances and photosensitizers that can interact with the active oxygen species and damage the cell, you get very high inactivation rates and very high rates of cell death. This is some work we did in the laboratory just to show you this. You can see here, if you're in the dark, this is K, the inactivation rate constant per hour. This is the wavelength that the inactivation rates have been measured at. You can see it's very low inactivation in the dark. And as you move up to the more reactive, shorter wavelength UV, you get higher inactivation. So it's a benefit to put the cells through higher UVB irradiances. And what we're showing here is that we've used a quencher, histidine, which quenches the reactive oxygen species. And when we look at the no quencher, when we've got the reactive oxygen species and the photosensitizers, we get higher inactivation rates than when we've got the quencher that removes the reactive oxygen species. And what we're showing here is these photosensitizers are present in wastewater and will increase the contribution of UVA to disinfection and also increase the application or the effect of visible light as well. So there's a good mechanistic basis for why we have higher inactivation rates in high rate ponds compared to waste sterilization ponds. And of course, I wanted to show some figures this time because I was asked last time about relative costs. This is work that was modelled by Neil Buchanan, another PhD student of mine, and you can see you can work through this at your leisure. But what we've done is costed out the earthworks, paddle wheel, etc., and comparing the high rate pond to the waste stabilization pond for the same scenario, it's actually 47% of the cost of the waste stabilization pond, largely because you're reducing the area requirement because you've improved the reaction rates by having the shallow system mixed with a paddle wheel. Further developments at Kingston-on-Murray, we've now turned this system just this year into a solar-powered system with battery-powered storage. And the battery is not a lithium ion, it's actually what's called a saltwater battery. You can look up aqua ion on the web. We've selected that because it's benign environmentally if anything went wrong compared to a lithium ion. But this now means that this system is being operated off grid and demonstrates its applicability for communities that are not close to line power. International engagement, we're also involved in the World Health Organization. They have a new sanitation safety planning manual. This is supported by something called the Global Water Pathogen Project. I'd commend this to everybody. It's a great site. It's been supported by the Gates Foundation and also Michigan State University. It's really trying to underpin the application of the safety planning manual. And why I think it's such a great site is if you wanted to know anything about the organisms present in wastewater, the nature of the pathogens present, the risks, and how you do a risk assessment, a quantitative microbiological risk assessment, it's really a great source for information. Where we're participating is there's a case study part to demonstrate how you use risk assessment to protect the public during from exposure to pathogens with reuse of wastewater, treated wastewater. And one of the case studies in this is the system in South Australia, with a view to the system being made more widely available and understood that it has been validated and it is a reasonable option for communities that have reticulated water and flushing toilets. And I had the pleasure to go and me peering over the array there to a case study meeting run by the World Health Organization, the Gates Foundation, really to talk about case studies from around the world. And I'd commend that site to you, the Global Water Pathogen Project. And I just put some acknowledgements up there. It's not all about me. It's about the people who've worked with me over the 10 years that this project has taken to go from research to adoption. And we are now looking at more systems being certainly constructed in South Australia for rural communities. Thank you very much.
That's excellent. Thank you very much, Howard. A terrific rundown and such a vast amount of work going on there. And ending up there, particularly with that solar-powered battery-supported unit at Kingston-on-Murray. That's absolutely brilliant. Look, a couple of logistics before we go to questions, and there's tons of them coming in, so I would advise getting in early, but we look forward to hearing from everyone. I just wanted to say that so good to see people from Kenya, Julia from Kenya, Mohammed Hassan from United Arab Emirates, and Welly from Indonesia, Zadias from Namibia, and Catherine Sylvester, who is the IWA Vice President, joining us from Sydney. It's just a great number of people. But look, let's get straight into the questions. First one from Tim Pryor, Howard. Tim's got a couple of questions here regarding recycled water management for HRAP systems. Number one, the HRAP effluent has high biomass concentration, which is kept in suspension by the paddle wheel. Once this effluent is discharged into a recycled water storage lagoon, which are required to balance winter storage for most of the reuse applications, the constant fluid motion will stop. Will this cause a high rate of sedimentation on the bottom of the storage lagoon? Could be a problem in cases with multiple storage lagoons and low-level transfer pipes.
Yep. Thanks, Tim, for the question. I mean, you're familiar, obviously, that the previous systems also had storage lagoons for irrigation. You will get settlement in those lagoons over a period of time, obviously, and it depends. Then I would suggest where you actually take the effluent for the treated effluent, the stored effluent for irrigation. I mean, that's a standard approach, no matter whether it's a high rate pond or a waste stabilization pond. It's management of the effluent and settlement. And you're quite right, you will have higher levels of suspended solids because of the high rate of algal production. And I think that's that should be seen as an opportunity rather than a problem. And I think as we have more systems, the question of what you do with the increased biosolids, and that was really when I showed the pond systems at Melbourne. The original research with Smart Water Fund in Victoria wasn't for wastewater treatment. It was to use the effluent to reduce biomass, and that biomass being seen as biosolids, would it enhance anaerobic? Could it be used to enhance biogas production in anaerobic digesters? And on larger systems, obviously, recovering that biomass and turn it into energy is another integration of wastewater treatment and energy production.
Thanks. Yeah, that's good. That's a great response. The second question that Tim has, Tim is from Walbridge, Gilbert, Aztec. Thank you, Tim, for these questions. It's really good. Supposing this sedimentation does not occur, the reused water drawn from the lagoon will still have a high concentration of biomass. So under current South Australian regs, the water would likely need to be chlorinated. So some filtration would be required for pre-chlorination to reduce solids loads. What filter screen membrane size do you think would be required based on your understanding of the HRAP effluent constituents?
Well, Tim, I'm probably going to do a body swerve here because I'm a microbiologist, not an engineer. And part of this understanding is that we're offering the high rate pond as an element in a treatment train, and the other systems and those removals I defer to my engineering colleagues in terms of what's best given the volumes of flow. I can provide information on the likely biomass that's going to be in the effluent. So I think it's part of a team that's designing the treatment train. And you've mentioned one site there, and I'm part of a team that would design that, but I'm not designing the whole treatment train. I think I'm master of some areas, but not all.
Yeah, no, that sounds good. That sounds good. Next question is from Ionet in Perth. Are there any policies regarding water quality, that is micropollutant concentration, for the WSP/HRAP effluent?
That's an interesting question because there's been very little work done. It's an area that I would really like to get some research up on in terms of what a high rip pond actually does in terms of removing micropollutants. There are some publications that indicate they're very efficient because they're highly aerobic environments. We have looked at. We took another tack years ago. We actually got ethics approval to survey the population producing the effluent, and we surveyed their prescription drug usage. And of course, we find out that in these smaller communities, somewhat sadly, they're populated by more mature people, and they tend to be taking things like statins and anti-inflammatories. And so that would be one tack, would be to look at what you think the population is likely to be exposed to, and then setting up some research to answer those questions based on that survey. The simple answer is there's none.
Yeah, no, that's excellent. Ionet also has a second question. There is a higher inactivation of pathogens in HRAP compared to WSP due to mixing. Do you have any information regarding the biodegradation of organic compounds in HRAP compared to other non-conventional wastewater treatment systems?
Well, it depends what you mean by organic compounds. I mean, the traditional measurements that we would use is the industry, standard really of BOD5, and in all conditions, including in the winter, we would get about a 95% reduction in BOD5 inlet to outlet, and it's the same. We've also measured TOC, total organic carbon, total carbon going through the system, and it's a very efficient removal mechanism for available carbon measured in that means of BOD and TOC.
Yep, that's great. I was referring to pharmaceutical personal care products. Yeah.
No, that's what I was saying, is that there's very little work. I mean, I would really like, if anybody wants to contact me and set up a series of research on the pond systems we have, given the compounds that I've sort of identified from that survey. There is very little work that's been done on that in waste stabilization ponds or high rate ponds. Certainly high rate ponds, very, very sparse information on trace organics and pharmaceuticals, etc.
Yep. About the course in November, got a question from Joe from Melbourne. The course in November is a 2-day course, a bit of field work, a bit of in-class work, but what is going to be in that course?
Well, what we would do, what we were planning would be to show you a community wastewater management system. We could take you visiting traditional systems and look at how they perform. Look at the layout and have a discussion. It's always better, I think, to see things on the ground and be standing adjacent to them, and get a feel for what they look like. So we would visit the Lindock system, hopefully, and look at the waste stabilization ponds there. Go on to our demonstration research site at Kingston-on-Murray, talk through that system. Again, on site with talk about the choice of solar power and what else we could do on that system. And we have other experiments and other research going on that system about the disposal and what's happening to soil quality, because we're disposal there to woodlot, and it includes the wastewater and the solids that have been produced in the high rate pond. We're looking at soil carbon, etc. So there's other things to see there and the measurements of that. We're also looking at the production of energy crops using the wastewater as an irrigation source, so looking to maximize. And then we'd have a bit more of the theory and the practice and the design of high rate ponds, and talk through those issues, the microbiology, the biology, talk more about the nutrient removal mechanisms, because I haven't had time to talk about that. I know some people seem they're keen to talk about nitrogen and phosphorus removal in these systems, and take you through the mechanisms of that. So it would be a rounded program of waste stabilization ponds and high rate ponds.
So this is going to be a great course. I'm really looking forward to it. The breadth of this and the impact of this work that Howard's been doing over a decade or more now is going to be talked about at these 2 days. And I, for one, am doing some planning to spend some time 2 hours east of Adelaide in South Australia, 3 hours east of Adelaide in South Australia, having a look at what's actually happening on ground, and then going to a nice lunch at a lovely winery on the way through, and then a classroom for an hour or two, but mostly dedicated to field work with 2 days of access to Howard, basically, and that's a mentoring opportunity which I really highly recommend. So, okay, that's the advert. We'll get on to some more questions, but you'll hear from us again on that. We'll email you about the details of that course up in November 22, 23. If you've got a diary handy, put it in. Here we go. Another question from Welly in Namibia. What time would it be in Namibia? Howard, don't even think of one. No, Indonesia. Sorry, Indonesia. No, it's only close to Australia. Here we go. Do you have any problems regarding the nitrogen and phosphorus, especially during summer and winter? For example, lack of nutrients during the rainy season / winter.
Well, okay. I mean, I think I said this in the last webinar as well. I think the high rate ponds really very efficient, and so are waste stabilization ponds really very efficient for nitrogen removal. So we would see nitrogen removal rates in terms of percentages from between 60 to 90%, 90% in the summer, 60, 70% in the winter. So they are seasonally affected in terms of nitrogen removal, and the nitrogen removal is a combination of uptake into really it's uptake into the biomass. There's some volatilization of ammonia that's obviously present in the system at those high pHs I indicated at 9 to 11 is when you're starting to lose ammonia because of the ammonia equilibrium. I think, and it's another area that I would like to do more research on, and I think more research is required, is I think we probably oversell these systems on phosphorus removal. And the phosphorus removal is quite poor, and I don't pretend that otherwise. We've had some work done recently. The phosphorus removal mechanisms, of course, are incorporation into the biomass, because we're looking at nitrogen phosphorus being fertilizer for the algae in effect. So the phosphorus is incorporated into the biomass, but it's very low. You only need 1 mole of phosphorus to produce a mole of algae. So that's a low level uptake. But you also see, because of the high pHs, and I think this is probably a bigger impact that we don't yet understand fully, it depends on the quality of the drinking water that is being taken by the community. And things like calcium, magnesium the other ions that will cause phosphorus precipitation within the biomass at those high pHs again. So I think we don't necessarily understand the interaction between the water quality that's being used by the community, the high pHs and ammonia levels that are in the pond system, and how that interacts with phosphorus removal. Because if you look at the data worldwide, you'll see very large variation in reported phosphorus removals, and I think it's more to do with water chemistry than it is to do with biomass production.
Yep. Look, we're coming toward our last 5 minutes of the 45-minute webinar, so we're going to take a last question right now. But before we do, I just wanted to say it's so good to see Dr. Syed Hamid in Karachi, Pakistan, with a group of all your students with us, and we're very glad to have you on board, Syed. We welcome you and your students, all one and all. Thank you for joining us. Just wanted to give acknowledgement to you there in Pakistan. So I think we'll draw this to a close. Joseph from Tanzania has asked one last question, Howard, if I may. What is the cost of installing and running of this system compared to other systems?
Well, that's another very good question. We've looked at it depends what you mean by other systems. Obviously, the waste stabilization pond has no energy input at all. It's just a static body of water. Once you've delivered the water there, that's the cost over with. But of course, if you mean things like activated sludge plants and membrane bioreactors, the energy consumption for a high rate pond compared to, say, an extended aerated activated sludge plant, it's at least a tenth of the cost in energy terms and greenhouse gas emissions. So I think from the point of view of the benefit of including a paddle wheel and being able to demonstrate that could be driven by a solar powered battery system means that you can really start to compete with those high energy consuming systems for what is an efficient passive wastewater treatment system.
Yep, no, that's great, Howard. Look, I did say it was going to be the last question, but there is going to be another one in a moment. But thank you, Joseph, for that question. I understand you're from Tanzania, a Ministry of Water and Irrigation, as a hydrogeologist, so we really appreciate your questions coming through on such a practical and scientific level. Phil Staniford, this last question, it's probably a short one, so I'll include this one now. Where is the outflow located in the trial ponds?
Yeah, the inflow normally, ideally, we would put it behind the paddle wheel, and we'd take the outflow from the furthest linear distance of channel distance from the inflow. Yeah. But I think I understand the question. That the tenet of the question is about whether we get hydraulic short circuiting if we're recirculating the effluent. Simple answer is we do, but you also get hydraulic short circuiting in waste stabilization ponds as well. Yeah. It's often not acknowledged.
Yeah, but no, that's right. You picked it.
We have done the modelling of this. We know that we can do modelling of particularly E. coli and FRNA phage removal that matches our practical measurements on site, and we'll be publishing the results of that work soon.
Yep, that's excellent. That's what Phil was getting at, residence times and short circuiting occurring. So that's great. All right. Well, that's all we've got time for today, and I appreciate everybody joining us. It's been huge. A day on top of the first webinar like this we did earlier on, later last year we did this webinar. But look, just to round off today, there's a feedback form coming up as soon as you close off. Be sure to tick the answers you'd like to those questions, and that'll help us shape this webinar for the future. A recording will be emailed to you. The link will be emailed to you. And these are the free webinars coming up. But I would like to highlight the course, November 22nd, 23rd. I wonder if we can shoot back to that, Joel, just to get that that PowerPoint up. Maybe not, but it's further up. There's a there we go. The fifth dot point on your screen now. High rate algal ponds community wastewater reuse. Wednesday 22nd, Thursday 23rd November, Loxton. We'll email you all the details. But I've put a strong word in for that. If you're able to come, that'd be fantastic. All right, well, that is all we have time for today. Be sure to join us next webinar on Thursday, 7th of September, if you're interested in managed aquifer recharge. But for now, we'll sign off. Thanks for joining us, everybody.
Thank you.